Hey guys, I'm going to use the bathroom real quick, and then we will first look at some corrections on the things that I said yesterday, and then we will continue with more integration techniques, specifically involving integration by parts, but a second way to prove our formula for the Gaussian integral and therefore the factorial of 1/2. So I'll be right back. All right, guys, how's it going?
Well,
Glad to hear it. Okay, let's scroll up. All right. So this was a 3 when I wrote it down. Should be a 6 because it's a factorial. And then let's see what the next thing is. I'm actually going to open a new page to the next one. Hopefully that will make the next piece in this less laggy. See, it's too big. It unloads parts as you scroll away from them. That's unfortunate. Maybe it's just too hot in my room. My computer's chugging. Okay. Also, I wanted to do more of these exercises. I wanted to find the derivatives of all the inverse trig functions today, because those are like the number one like gatekeeping integrals for people. If they want to give you something that's hard, you don't know how to do it without having some context that that's what you should do, then the that's a very cruel question to give, I guess. So let's also look at a mistake I made here. When I wrote the recurrence relation for the gamma function, it was incorrect. It should be gamma of n is equal to n minus 1 times gamma of n minus 1. And then I also said this integral is defined for things that are not a negative integer, but actually this integral is not defined for things that are not a negative real. And or I think n should be greater than 1 here. Greater than or equal to 1. All right, draw, please. It won't give me the pens. Oh, n is greater than or equal to 1. I need my colors back. What just happened? We might be stuck with pink. Okay. And this recurrence relation allows us to extend it to non-integer real numbers. But then we would ask, okay, so what is gamma of 0? So we would have gamma of 0 times 0 is equal to gamma of 1. So that means that gamma of 0 is equal to gamma of 1 divided by 0. That doesn't make sense. And for this reason, there are poles of the gamma function at every non-positive integer, but it is well defined everywhere else in the complex plane. So I think that was it for this page. There might have been one more like sign error that I made, but show all. Let's do a new stuff. New page. Come on.
I was able to get arc cos and arc sine, like the derivatives.
Mm-hmm.
Wasn't that part of our homework? I wasn't able to
Yes.
get cosh and sinh.
Okay. Okay, I wish it would let me open up a new page. Do I have to delete an old one? Here, let's try just deleting a really old one. Don't make me go to Active Inspire. All right, we're going to do Active Inspire. New flip chart. Okay, so tell me what you got for arcsine or arc sine and arc cosine.
Arc sine is 1 over rad 1 minus x squared, and then cos. I didn't actually do cos, but I just knew from the graph that it's like a negative, and then I guess translate it down, but the translation doesn't matter. So it's just a negative derivative of arc sine.
Yep. Yep. And so arc sinh. Oh, I wrote these twice. Arc sinh and arc cosh are very similar. Okay. And first of all, in order to solve these the way that we solved them, we had to draw a hyperbolic right triangle. So, or hyperbolic triangle. Here we're gonna have to draw a hyperbolic right triangle, and it's pretty easy. And so all the assumptions about angles that we made about triangles in the Euclidean case are going to be valid in this case. So even though angles aren't well defined in the greater hyperbolic plane, for solving these, they suffice. So it's a theorem that for any type of geometry, if you have a line that is tangent to a circle, then it's perpendicular. So let's say I wanted to draw a triangle with a right angle at this point. I would just do this, and this would be a hyperbolic right angle for this triangle. But actually, we can do a little better than that. If we look again right here, where this thing intersects the x-axis, the perpendicular line looks like a Euclidean perpendicular line. So if we draw a triangle right here, we can just draw a line parallel to the y-axis, and that's still a hyperbolic right triangle for this particular angle, theta. So it definitely depends on the orientation, because there's no way that I could draw this in hyperbolic geometry and claim that that's a right triangle, but it doesn't matter. So let's, with that out of the way, meaning that we can just draw the same exact right triangle, let's actually solve this problem. So we have d dx. Let's actually just, before we take the derivative, say that arc sinh of x is equal to y. That means that sinh of y is equal to x. Now we take the derivative with respect to x. So then we get cosh y times y primed is equal to 1. And so y primed is equal to hyperbolic secant of y. So if we draw a triangle, we were saying that arc sine or arc sinh of x, so that means that this is x and this is 1. So that means that according to the hyperbolic Pythagorean theorem, if this is A, this is B, this is C, where you specifically have that this is the x-axis and this is the y-axis, then the hyperbolic Pythagorean theorem states that a squared minus b squared equals c squared. So we get that this length down here is 1 plus x squared. And so y primed, which is the quantity that we're looking for, is 1 over the square root of 1 plus x squared. And this is the same thing as saying that the integral of dx over the square root of 1 plus x squared is equal to arcsinch plus a constant. And this is really helpful. However, there's something that is going to be difficult for this integral to find a series out of it that wasn't present when we were doing inverse tangent. Someone think they could tell me what the difficulty of pulling a series out of this integral is? Well, if you remember, the way that we did it with tangent is we used a geometric series, but here we have a square root. So you will need to know Newton's generalized binomial theorem, which we really should talk about, but it's not strictly integration. So let's do the same exact type. Let's see. I'll leave hyperbolic cosine as an exercise still, but these are all good things to know what their derivatives are. And now let's talk about a
Going strictly based on arc cos and arc sinh, is it just -1 over
yeah.
root 1 plus x squared?
Mhm.
Okay.
All right. So then let's talk about just an important formula that we'll use later when we're summoning the gamma function. Let's find an antiderivative of this integral. And so let's use integration by parts. So I want you to try this for a second and see if something unexpected happens. I'll start doing it slowly, but I want you guys to try it, see if just what pops out. Okay, and so here we get that this is equal to so is this really a better than what we started out with? Because it looks like we just turned this problem into sort of an equal problem, right?
Yeah.
So what should we do about it?
Can you integrate again?
Yes, yes.
Wait,
You
really?
use
Oh, okay.
that's pretty much exactly it. You just use integration by parts again. You know, a normal person would reach this point and they would throw their hands up because they have been handed, you know, the same thing. They would say integration by parts has left me, it's abandoned me. But nope, you just have to have patience and do it twice. So I'm going to pull that one out of A out, and then we're going to say that u is equal to cosine of x. So du is equal to minus sine of x. And dv is equal to e to the ax. dx. So v is equal to e to the ax divided by a. And so this new integral, let's scroll down just a little bit more. We're going to end up with 1 over a e to the ax minus, in parentheses, e to the ax over a cosine of x minus, then this integral has a minus sign in it, so it becomes a plus. That's e to the ax sine of x dx. So what we have is integral e to the ax sine of x dx is equal to, I'm going to pull an e to the a out of these things. So e to the ax times, oh, there should be a sine x on this, shouldn't there? Let's rewrite that. Okay, so we have sine of x. And then in order to combine denominators, I'm going to multiply this by a. So I maybe should have a sine of x minus cosine of x over a squared plus 1 over a, that should be squared. So there's a 1 over a on the outside of this thing.
My doorbell just rings. Okay, come right back.
Yep. And we distributed a minus sign, so that should be a minus sign. E to the ax sine of x dx. So now, even though we don't know what our integral is, we have obtained a scaled version of it on the other side. So we just add it to both sides. I'm just going to plus I. So we get 1 plus 1 over a squared integral e to the ax sine of x dx is equal to this thing here, that is e to the ax a sine of x minus cosine of x over a squared. If we multiply by the reciprocal of 1 plus a squared, then we get the integral of e to the ax sine x dx is equal to e to the ax a over sine of x minus cosine of x over 1 plus a squared. So it's good to take note of this formula, not for like general use. For if you generally run across one of these, you should just integrate by parts, but you should write down this formula because we're going to use it again in this discussion. So I'll just wait for Ashrith to get back. Or maybe I'll start doing the same thing for cosine. The cosine formula is really familiar. I'm pretty sure it's the other way around. All right, let's do it for cosine. So I'll go faster for this one. U equals cosine x, du equals minus sine of x, v equals e to the dv equals e to the ax dx. So v is equal to e to the ax over a. So this thing is equal to e to the ax cosine x over a minus 1 over a integral of, that's minus sine of x, that becomes a plus sine of x, and that is going to be an e to the ax dx. Okay. But we know that this is equal to 1 over a. Let's write, I don't want to skip too many steps. Okay, e to the ax cosine x plus 1 over a integral. We're going to do it again. U is equal to sine of x du is equal to cosine of x. dv is equal to e to the ax over a dx. So v, oh, that shouldn't be over a. V is equal to e to the ax over a. So we get e to the ax over a times sine of x minus 1 over a integral that we started with. Okay, so what we end up with is one of these minus signs should have canceled. Plus, oh, no, we're good. We're good. So we get 1 plus 1 over a squared times our integral e to the ax cosine x dx is equal to e to the ax over a times, I guess I should put this on the outside, e to the ax over a squared. It's going to be a cosine x plus sine x. So yeah, you just flip them and you change the sign in the middle. And if we just simplify this equation, e to the ax cosine x dx is equal to this thing. All right, that's a pretty nice integration trick. So let's do some other examples of integration by parts. Let's just see some neat integrals that you can solve by integration by parts. Here, let me grab, I had a huge list of examples that we could go through. All right, who wants to tell me how to solve or find an antiderivative of x cosine x? Well, we really would like this thing to go down. If the degree of the polynomial term goes down, then our integral becomes easier. So we could say that u is equal to x. So du is equal to dx and dv is equal to cosine x dx. So v is equal to minus sine x. So we have that this is equal to minus x sine x minus the integral sine of x with a minus sign going out front dx. So plus c, because this is an antiderivative. And I guess we should have not forgotten the plus c on that. There you go, little plus c. So integral from x cosine x dx is equal to minus x sine x minus cosine x plus c, because the antiderivative of sine is minus cosine. Ooh, come on. So then how about find an antiderivative of r cubed natural log of r dr? So what's the difficulty here?
I'm
Ellen.
writing it down slowly. Sorry.
Yeah,
Do you,
no.
like,
I mean,
give us
I'm asking like a sanity check, like just to motivate why we're using integration by parts here. But yeah, take your time. But so my question is what's the difficulty here? How is integration by parts going to help us? Just to, because there's no hard and fast rule to know when to use integration by parts. We just want to identify situations where it's useful.
Getting an or doing a derivative and getting a natural log is hard, at least from what I've seen.
Actually, let's do this example first. What's the natural log, a derivative of the natural log? derivative. What's the integral of the natural log? So here we're going to be really sneaky. So let's set u equal to natural log of x. So du is equal to 1 over x dx, and dv equal to dx. So that v is equal to x.
Is it x ln x minus x?
Yep. Wait. So this is equal to x ln x minus the integral of, yep, minus x. So plus c equals x ln x minus x plus c. That's pretty neat. So we've conquered that difficulty. What's the difficulty here?
So v is equal to the integral of ln x, or ln of r. Or am I doing this wrong?
I think you got cut out there.
Hello?
Well, I heard the ending of it, but did you set u equal to r cubed?
Yeah, I said u to the r cubed, and I got v is equal to the integral of ln of r.
ln
Yep.
rdr.
Yep. So v is equal to x ln x minus x. We'll say that's the antiderivative we're choosing.
Am I quiet or can you hear me?
I can hear you now. Oh, okay. So actually we do have to do the plus c, and this will show how general do you want this formula to be? Do you want to get a particular antiderivative, or do you want to see like the class, the whole family of antiderivatives of this integral? The arithmetic is going to be uglier if we get all of these arbitrary constants floating around. So I'm just going to set c equal to 0. I mean, that's what we usually do with integration by parts, but yeah, let's just do that. So we get that this is equal to u is equal to r cubed. Ooh, maybe I should write that in terms of r. R ln r minus r. So this is r to the 4th ln r minus we have 3 times the integral r squared ln r dr. So the big idea for this exercise is that we use the product or integration by parts as a power reduction formula. So this becomes r squared times r cubed ln r minus, this should also be r to the 4th, okay, minus ln r cubed minus the integral r ln r dr. So we get equals r to the 4th minus ln r minus r to the 4th minus 3 r cubed ln r plus 3 r cubed plus 3 times the integral is going to be r squared ln r minus r squared, and then minus the integral of ln. So that is going to be r ln r. Oh, we got to multiply it by 2 though. 2 times ln r ln r minus r. And then we can just have a plus c on the outside. So if we simplify this, we get the r to the 4th minus 3r cubed. Is that another minus sign? Let's see. Yeah, that should be a minus sign here. That's a minus sign. Okay. Minus 3r squared plus 2r, no, plus 6r times ln r. And then I'm pretty sure we're going to have minus the same polynomial, minus r to the fourth minus 3r cubed minus 3r squared plus 6r. I don't know the general pattern actually. That would be a good exercise to find the general pattern. There's probably an integration table out there somewhere where someone has found a more general antiderivative like this. It'd probably be way uglier if we kept those c's in there too. Okay, let's look at the next one on my list. We'll do one more example with the natural log. So what should we try here? So the problem with this is if we use integration by parts, it's going to lower our degree. We could try doing integration by parts to raise our degree. So for instance, we could say that u is equal to ln y. So du is equal to 1 over y dy. dv is equal to root y dy. So v is equal to, the integral of that is going to be root y over 2. So if we, now when we do our integration, it's going to be kind of nice. Let's be y ln y minus the integral, because now we're getting just,
Wait, are you sure for that integral?
so what I used here is this rule. Dx is equal to,
Yeah, I know. That's why the 1/2.
oh,
isn't
that
it?
should be -1 there.
Yeah.
There we go. There we go. So 1 over root y dy. There we go. Apologies for the confusion. So this integral is much easier to do if you can write it correctly. So ln of y over root y dy equals root y over 2 ln of y minus, that is root y over 4 plus c. All right. So what about this integral? Let's say arc tan of x dx.
I think you already showed this to us. This is 1 over 1 plus x squared.
That's the derivative.
Yeah, we showed this
wait,
one.
okay, wait.
That's a good thing to keep in mind. That's an important thing to keep in mind for this, but we saw this one. So we don't know how to integrate arctan yet, and asking how to integrate arctan for integration by parts is foolish. So let's try to make that our u. So then our dv, let's make that dx. So that v equals x. And we get that this thing is going to be x arctan x minus the integral of x dx over 1 plus x squared. So actually, this integral is way easier than the arctan integral was. Well, the arctan integral, you kind of just have to know what the derivative of arctan is. But you can tell me the trick for this one? Minus right here, x dx over 1 plus x squared. I'm going to move this closer over here so we have space to write here. What do we do to that thing?
Can you integrate that by parts and then call what? V 1 over x squared dx? Oh, 1 over 1 plus x squared dx. And just make it arctan.
At this point, we should see that a u substitution would be appropriate here. For rational functions, you don't really want to apply integration by parts, except if it's a specifically designed integral. We'll see how to deal with rational functions in general. It turns out that if you just have if your function is the ratio of two polynomials and you can factor the denominator, you can always integrate it. But this one is actually a u substitution. So
I forgot about that.
It's all right. I mean, taking derivatives is relatively easy. Doing integrals is a lot harder in comparison because there's a lot less like overarching principles that you can use. So that is equal to the natural log of u, right? That should be an x right there. Arctan x minus 1/2 the natural log. We said u was 1 plus x squared plus c. All right. So let's do, what is this integral? Dx. Should have put the dx there. It actually means something without the dx. So we know that if u is equal to arc hyperbolic cosine of x, then du is equal to -1 over the square root of 1 plus x squared. And if dv is equal to v, then v, is equal to dx, then v is equal to x. So we get here x arc hyperbolic cosine of x minus the integral, but here we're going to turn this into a plus sign because we have a minus sign here, dx over the square root of 1 plus x squared times x in the numerator. All right, so what are we doing to this thing?
Can you also do u substitution?
Yep. Exact same u substitution. Oh, not cos, cosh. Plus, so this integral is going to be 1/2 the natural log of the square root of 1 plus x squared. No, that's not true. That's not true at all. That's not true at all. The integral of du over the square root of u, which we said was the square root of u over 2. So this is equal to x arc cosh x plus square root of 1 plus x squared over 4 plus c.
Isn't? No, never mind.
Feel free to point out any mistakes I make. I really welcome it. But that looks correct to me.
Is there a
Yes, it
negative?
is.
Is there a
way.
negative?
No,
No.
I think, yeah, never mind.
You got rid of the negative by adding 1.
All right. So for homework, do integration by parts on the other inverse trigonometric things. So, Okay, so we have 20 minutes left. I'm going to save some of the integration by parts where we're going to think of it as a power reduction formula in the context of powers of sine, cosine, and natural log for next time. And let's learn a different kind of technique for integrating that will let us revisit the gamma function and prove it without using polar integrals. Prove that the factorial of 1/2 is the square root of pi over 2. Even though there is more we should say about polar integrals and how exactly we got that formula, even if you define some other coordinate system, how would you find their stuff without being or without having advanced knowledge of trigonometry? Let me just find the paper where I wrote this down. It may no longer exist. Okay, we can just do a freehand example here, actually. All right. So this method was invented by Leibniz. And it's called differentiating under the integral. I think integration by parts was also invented by Leibniz, even though it was known to Newton later. So let's say we have a function f of x and t, and I'm going to say that is nice. Okay, so this is where I'm waving my hands and being less rigorous. If f of x and t is nice, then we can do this. Dx, we can first evaluate it as an antiderivative in x, and then take the derivative. So we get df dt. Or we can take the derivative first and then integrate in x, and we arrive at the same conclusion. So this means that sometimes one path is more desirable than the other, and it also means that sometimes we can solve problems by turning it into a more complicated problem and then solving that one. So let's look at a really simple example. 2x plus t cubed squared dx. So an antiderivative for this thing is 2x plus t cubed. Actually, let's integrate this correctly. Let's not skip any steps. So u is equal to 2x plus t cubed, du is equal to 2 dx. So this is equal to 1/2 the integral from 0 to 2 plus t cubed. So I should put a t cubed here, actually. Of 2x plus, wow. You know what? I'm just going to look at the antiderivative. We don't care because we're going to turn it back into x's. So that's going to be u squared du. So this is equal to 2x plus t cubed to the third over 6, evaluated from x is equal to 0 to 1. So I guess I should specify that. So that is equal to t, we're going to have to expand this eventually. So that is equal to t to the 9th plus, that is 6 t to the 6 x plus 12 t cubed x squared plus 8 x cubed. But that is evaluated from x equals 0 to 1. So that is going to be the t cubes, or t to the 9th are going to cancel out, and we're going to be left with t to the 6th plus 2t cubed plus 4 over 3. All right, so this is a really simple example. I'm just demonstrating that this actually works. So now let's take the same integral and take the derivative with respect to t and then integrate it with respect to x. So 0 to 1 d dt. Oh, wait. We got to take the derivative of this. So we integrated it. And now if we take the derivative, we get 6t to the 5th plus 6t squared plus 0. Okay, so now let's take the derivative first. Cubed squared dt, that is equal to the integral of 2 times 2x plus t cubed times, according to the chain rule, 3t squared from 0 to 1 dx. So that is equal to the integral from 0 to 1 of 12x t squared plus 6t to the t to the 5th dx. And so this is 6x squared t squared plus 6x t to the 5th, evaluated from x equals 0 to 1, which is the same thing as we got before. 6t squared plus 6t to the 5th. Okay, great. So let's actually use this to solve, to revisit our friend, the gamma function. Well, first, let's look at this integral. So the integral from 0 to infinity of minus t, or minus x, I should say, x dx. Can someone tell me what this is equal to? So this is minus e to the minus x, evaluated from x equals 0 to x equals infinity. So if we plug in x is equal to infinity, e to the minus x goes to 0. So that's minus 0 plus, if we plug in 0, we get 1. So we start with this, minus x dx.
Wait, wouldn't you get -1? Oh, minus -1. Right, sorry.
It's all right. It's all right. We definitely all make mistakes. I feel like I make most of the mistakes, but I don't see the work that you guys do. But anyway, so now let's recover our friend the gamma function out of this. So let's change x to tx, and then that means that dx is equal to t dx, or we have to resend it there. Okay, so let's rewrite. So we get 0 to infinity e to the tx, t dx equals 1. Now, since t is constant with respect to x, we can divide both sides by x. If we were thinking as t as a constant from the beginning, this is still what we would have gotten from this integral, so that's fine. Now let's use Leibniz's idea to differentiate under the integral. So if I take the derivative of this thing, it's going to be equal to the derivative of this thing. Actually, let's say that t is greater than 0 and this is minus. There we go. We want a minus sign on this. So then this becomes a minus right here. And do we want a minus on that? Yeah, that's still fine. No, the minus was on the x correctly. That's what I didn't do. The minus was always here. I just didn't rewrite the minus sign when I did the substitution. Okay. So this is still the correct substitution. We want t to be greater than 0 so that the integral makes sense when evaluated at 0. So t is greater than 0. And then this is correct. So we have this. So if we take the derivative here, we get 0 to infinity. There should be a minus sign. Minus t e to the minus tx dx. Nope. If we take the derivative with respect to t, the chain rule says we should get a minus x here. Minus x e to the minus tx dx is equal to minus 1 over t squared. Or another way of saying that is the integral of x e to the minus tx dx from 0 to infinity is equal to 1 over t squared. So we actually could prove this by integration by parts, but we kind of got it for free just by differentiating under the integral. Can someone confirm for me using integration by parts that this is what we get? Do you guys want to go a few minutes late today? I don't have anything after this. Let's just finish recovering the gamma function, at least.
I can't. My parents are slightly mad at me.
Dang. All right.
Funnily enough, it's in relation to this class.
Oh, did I do something wrong?
No, it's just my attendance.
Mm.
Like the fact that I'm here.
Well, then I feel way less bad about that. Keep doing math. So if we take the derivative of this thing with respect to t again, dx equals d dt 1 over t squared. Then we get integral of 0 to infinity minus x squared e to the minus tx dx equals 2 over t cubed. Minus sign, but then we make this a plus. And then if we take the derivative again, we get 0 to infinity x cubed e to the minus tx dx equals 6 over t to the 4th. And the pattern is if we take our derivative n times of e to the minus tx dx. That is equal to 0 to infinity of x to the n. I should say, if we have this equation, then we get this new equation, e to the minus tx dx is equal to n factorial over t to the n plus 1. And then if we just set n equal to, or sorry, t equal to 1, then we recover our friend the gamma function. X to the n e to the minus x dx is equal to n factorial. However, this method did not give us the recurrence relation for the gamma function, right? Or this is gamma of n plus 1, I should say. So you still need to use integration by parts to get the recurrence relation, but this is one way of getting it. And we're also going to use the same technique to find gamma of 3/2, which is 1/2 factorial. So dang, we ran out of time. So something to look forward to before we compute moments of the Gaussian integral. So we're going to solve the Gaussian integral another way, basically. So we're going to use the same thing here. But here, I'm just going to write down 2 integrals I want to solve next time using this, and then I'll let you guys go. This is solvable in elementary functions. And then one thing that I don't know if we're going to actually touch on, but actually this integral, you have to use series to define its antiderivative. It's not, you can't use elementary functions to satisfy it. And then we want to do this one, 0 to infinity of e to the minus x squared over 2. So last time we didn't have that over 2. We want to prove that this is equal to the square root of pi over 2. So we're going to use this trick of differentiating under the integral sign all those times to do it. For this one, we're going to get the, by the way, that this is equal to pi over 2 minus arctan of t. So that's all I have for you for now. We do have to schedule makeup classes. We could either have 1 extra week of math in the summer, or you can have extra math classes. Or if you want me to do a 2-hour long lecture on a weekend, I guess, just let me know. But just be thinking about that. You want extra math classes 1 week? Do you want to do an extra week of math? Or do you want to have a weekend lecture? But you can figure that out on your own time. For now, you're free to go.
Have a good day.
Later.
And
Corbin?
an extra week works better for me.
All right. What's up, Ashith?
Yeah, I agree with that. I kind of just already did the homework, but not really. I did the integral of arcsine x. Can I
Okay.
just run it by you?
Oh yeah, I also did that.
It
Alright.
is fairly similar to
Yeah, it's
arc
x
cosine.
arcsine x.
Wait, let's let Ashith say it.
Oh, sorry.
It's x arcsine x, and then pretty much the same thing. The second part is the same thing as cosine. So it's plus square root of 1 minus x squared over 2.
Yeah.
Over 2?
Oh no, I didn't get over 2.
It should be over 4, I think.
Oh?
No, it's over nothing.
Let's go
Why?
back. Well, then I might have made a mistake with the cosine one. So let's look at that. Don't you have a 1/2 here from dividing by 2 when you do the u substitution?
No, I don't think he did. He didn't do the hyperbolic one. He did non-hyperbolic.
But either way, you're still getting this x, right? So I'm talking about the u substitution.
No,
for
I
this integral.
think Matt's right.
Yes.
All right, I'll check
I
it.
don't think there's anything.
You get minus root 1 minus x squared.
Because if you just do the derivative of square root 1 minus x squared, you get what you need.
Okay. I will check myself then and not complain about it if I'm wrong.
Wait, do you want me to like write my thing out?
Sure, go ahead.
Okay. Speed run.
Yeah, if you just derivative of that right there, it works.
I said u.
Because the 2 from the within the u, from like the within the function, cancels out the 1/2.
Yes. Yes. That's perfect. Then d.
Thanks, Matt.
1 over plus. And then v. Yeah, dv.
How do you feel about the A/B test coming up?
I'm pretty prepared.
Yeah,
Yeah.
I think.
it's not like it's an Amy or anything like that.
Yeah, I'd get like if it was measured on the AP scale, I'd get like a 2 on the AP. I don't think I'd be passing. What would 6 be? Is it measured linearly?
I guess, but I feel like the AP test is like so much easier than the Amy that it uh shouldn't be linear, I guess, because the distribution of scores is probably different.
I always
Yeah,
make no
that's-
mistakes. So
Because I think 6. Yeah, 6 was above average this year.
Mhm.
I'm probably gonna
So
end up getting
that might be passing.
I'll probably end up doing like a dumb mistake on the AP test. I'm just gonna score over. Like basic division fails.
I think I got a 5 on the AB and a 4 on the BC. But that's just because, yeah, 4 on the BC. I didn't have a teacher for that class. It was self-study. That's what I'll say.
Oh,
Oh, that's pretty cool.
That is
It was less cool. It was just me hanging out in a classroom with 2 valedictorians.
I know my brother self-studied like I think macro or microeconomics, one of them. Or like self-study class is hard. Like how does it work?
It's not hard. Basically the teacher would just say, I want you to solve these problems at the end of 2 weeks. And the 3 of us would just sit down and figure out how to solve them.
I see.
nice. So sorry for the background noise.
All right.
That's I did a dumb again.
Well, I gotta go eat. So thank you.
Later, Ashes.
It's yeah.
So u equals 1 minus. So d u. Oh yeah, we gotta go further. So then you just factor out a negative 1 over 2. You get du. Just that over u, over root u. And that's just u to the negative 1 over 2. So it'd be 2 u to the 1 over 2. And then that cancels, that cancels. So it'd be minus rad u plus c. And then u is that.
That looks right.
All right.
Yeah.
I also have to go. All
All right, later.
right, later. Have a good day.